right, guys, so we're picking up with our second type of aqueous solution reaction, and it deals with acids and bases. So we're going to define acids and bases first, then we're going to look at our aqueous reactions with acids and bases. It's nothing new. Acid-base reactions, for the most part, that we're going to look at initially are double displacement reactions. So acids and bases have been used forever. Okay, alchemists were using them to try to do different things. Alchemists did a lot, but the main thing everybody gives alchemists credit for trying to do is turn less precious metals into more precious metals. They were more than that, but still they were using acids and stuff to try to do that. Romans used nitric acid. They actually called it aqua fortis, which Latin roughly translates to strong water, all right, to etch copper. And the reason they called it strong water is because acids are aqueous solutions. So they look like water, but they would take this water-looking sample and they would pour it onto copper and it would eat a hole into copper. And therefore they gave it the name aqua fortis. Now, one interesting thing that Romans would do is they would add acetic acid, which is vinegar. So it's acetate. All right, I'm going to show you both ways to write acetic acid. All right, here is C2H3O2 minus. This is acetate. The inorganic way to write acetic acid is to add a hydrogen. The hydrogen being the positive, so HC2H3O2. The more common way of seeing it written is the organic way, which is this here, CH3COOH. Okay. Now, what they would do is they would take acetic acid, vinegar essentially, and add it to their wine. And the wine would taste, so they would add this to wine, and the wine would end up being really sweet. And it's really weird because if you had vinegar before, which we all have, it's a really bitter taste. So why was the vinegar essentially being added to the wine making it sweet? And what was really happening was a double displacement reaction. They didn't realize it, but the majority of their containers at the time that the wine was held in was made out of lead. So they were doing a reaction and getting lead acetate out in their wine, which all acetates are soluble, so it wouldn't have precipitated. But the good news is lead acetate tastes sweet, so they would get a sweet tasting drink. The problem with that is it's lead. They were giving themselves lead poisoning by adding the vinegar to their wine to make it sweet, or adding it to water to make it sweet. They were getting a compound that tastes sweet, but it's full of lead. So what they were really doing is using an acid to, what they thought, make their drink taste better, but they were really poisoning themselves. Which is just an interesting side note in case you're ever on Jeopardy and you want to give me a shout out. Okay. All right. So, only if you get the question right. If you get the question wrong, you did not learn chemistry from me. Let's talk about what makes an acid and what makes a base a base. Okay? All right. First, we're going to look at what's known as the classical or Arrhenius definition. Okay. And what a classical definition deals with is how do I behave in water? What happens when I am placed in water? Now, the general form for an acid, I'm going to use red for acid, blue for bases. The general form for an acid, under the classical sense, is HA, where H is hydrogen, of course, and A is some anion that makes it an acid. If I place my acid into water, the classical definition says, an acid when placed into water will give me, and here's the key, hydronium. This is an ion with a water with an extra proton, an extra hydrogen, known as hydronium, plus whatever my anion is. Okay? So I'm an acid under classical definition if I'm placed into water and create this thing right here. Under classical definition, here's the general form for a base, and I'll use blue for a base. The general form for a classical base, this stands for some metal that makes hydroxide soluble. The classical definition of a base is if I place it into water, I dissociate. I break down. I'm a strong electrolyte or even a weak electrolyte, but the key is I will separate into my ions and I will create hydroxide. Plus, then I'll have some metal here. The metal has to make the hydroxide soluble. So group 1 metal, potassium hydroxide, all right, sodium hydroxide, lithium hydroxide, barium hydroxide for that matter. Okay. So that's the classical definition. How do I behave in water? An acid, I should write that this is an acid, will create hydronium. A base will create hydroxide. Okay. Any questions on that so far? So once we could decide whether we're an acid or a base, we could break down our acids, so we're going to deal with acids now, into 2 categories. Okay. Strong acids and weak acids. Now, strong and weak doesn't mean, well, if I'm a weak acid, I could essentially pour it all over myself and bathe in it. Weak acids should be handled with care just as strong acids. What strong and weak mean, all right, is the same thing as a strong electrolyte and a weak electrolyte. How much breaks down or dissociates. A strong acid 100% dissociates, breaks down. A weak acid only partially dissociates. Means you don't get the most hydronium for your buck. So if I put a 1 molar solution of a strong acid in water, or 1 molar, I should say, not solution, but 1 molar substance into water to make a solution, all of it will break down. I'll get out my maximum amount of hydronium, 1 molar, or depending what the ratio is. A weak acid won't do that. Now, there's a lot more weak acids than there are strong. So if you learn the rules for strong acids and they don't follow those rules, they have to be weak acids. So the first type of strong acid, there's only 2 types, are hydrogen bonded to a halogen. Now halogen is group 17. There is an exception to the rule. Okay? My exception to the rule is fluorine. Fluorine is not a strong acid when it bonds to a halogen. So, my strong acids based on the halogen, HCl, and again, they have to be in water. I'm not an acid until I'm in water. HCl, HBr, and HI. These are all strong acids. HF is not. So number 1, I'm a strong acid if I'm in water and I'm a hydrogen bonded to a halogen. Number 2 is if I'm an oxo acid. And what that means is I contain oxygen in my formula. Examples, okay? H2SO4, HNO3, but I'm an oxo acid and there's a little caveat. I need 2 more oxygens than hydrogens. So, H2SO4, HNO3, HClO3 are all strong acids. The difference between oxygen and hydrogen is 2. The difference between oxygen and hydrogen is 2. The difference between oxygen and hydrogen is 2. As long as I have 2 or more oxygen than I do hydrogen, I'll be a strong acid. All right? Now, again, there's a lot more weak acids. So, what are my weak acids? So, if I know the rules for my strong, the weak acid rules don't really matter, but let's just put them up there. Well, let's put the exception up there. The exception is that HFAQ. So, that's number 1. Number 2, what if I don't contain a halogen or an oxygen? Well, if I'm an acid and I don't contain a halogen or an oxygen, if I don't follow the strong acid rules, then I am considered weak. And examples of those are H2S, HCN, so these are weak. Number 3 is my oxoacids. Okay, that don't follow the rule. We'll put a line here and we'll just say it has less than examples of that: H3PO4, H2SO3, HNO2, okay, and number 4, organic acids. And organic just means they have carbon in them. So acetic acid that we looked at is weak. HC2H3O2. But again, you're most commonly going to see it written in the organic way. So if I see this like that, CH3COOH, I know I'm an organic acid. Where students get it mixed up with bases, they see this OH and they think it's a base. Don't do that. Remember, my base has to be bonded to a metal to a hydroxide. These aren't metals. What's really going to happen here is this hydrogen is what's going to be donated, and this is going to be left behind. This is not a hydroxide. Okay, so your strong acids, hydrogen with a halogen that's not fluorine, so HCl, HBr, HI. Oxoacids that have 2 or more oxygen than hydrogen. And my weak acids are everything that doesn't follow these 2 rules. And again, all of this is on the slides. But I figure, hey, earn your paycheck. Do some board work. All right, questions on how to tell if an acid's strong or weak. All right, so then let's talk about naming our acids. And here's why I want you to be familiar with your polyatomics, because it's going to come up here. All right, naming our acids. Let's start simple. HCl gas. Okay, this would be hydrogen chloride. If I put it in water, okay, and I make it HCl aqueous, which of course we know is going to break down, but if it was written like this, now I'm an acid because it's AQ. I take the prefix of hydrogen and make it hydro. I take the root of my anion, chlor, and add ic acid. So you have the prefix, the root, and the suffix. Okay. So what would HBr be as an acid? How would we name HBr? Bueller. What do we think? Hydrobromic, and don't forget the ending, Elena. You got it. HCN. Okay? We got to remember that this is a polyatomic known as cyanide. Hydro, cyanic, acid. Okay? So root, prefix, suffix. Now where the polyatomics come into play and it's important is here. Okay? Acids naming, this time with oxygen. If I contain oxygen, that means I'm with a polyatomic. H2SO4 aqueous versus H2SO3 aqueous. First thing, I want to make a note here. No hydro. No prefix. Get rid of the hydro. No hydro. Actually, putting a line through no hydro means hydro. So I'm just going to put no hydro. All right, so we need to remember that this is sulfate and this is sulfite. Just to point out, The one with sulfate is a strong acid. The difference is 4 minus 2 is 2. The one with sulfite is a weak acid. All right, so this is going to be a weak acid. This is going to be a strong acid. Sulfate, sulfite. 3 minus 2 is a difference of 1, weak. 4 minus 2, difference of 2, strong. Now, we don't use hydro. We take the root of our polyatomic. In our case here, the root is going to be sulfur. It's going to be the whole thing of sulfite. All right. If I end in 8, I become sulfuric, and then I add acid. 8 is ick. Ite becomes OUS, acid. Ite, OUS. The way I remember is either 8, I ate too much, ick, which we've all probably been doing since we've been stuck in the house. Ite, OUS, or you could say the one with the more oxygen, the higher oxygen number, high I, lower O, however you want to remember it. So this is nitrate, and this is the ite, which means this will be nitric acid, and this will be nitrous acid, okay, so knowing your polyatomics is going to be helpful when doing this part. Now there's one crazy one out there. Well, there's a couple, but the one that's most commonly shown and used is chlorate. So my versions of chlorate and its derivatives are the following as they appear as acids. I have HClO, HClO2, HClO3, and HClO4. Now, if you remember when we were doing our polyatomics, okay, the anions here, this is chlorate. I'm not writing the acid out yet. I'm just writing what the anion is. That would make this chlorite. That would make this hypochlorite. And that would make this up here one more than the 8 per chlorate. Running out of board space here. I'll just write it down a little bit further. I'm still going to screw myself up here, chlorate. Yep. All right. So I have chlorate, one less oxygen made it ite, another less makes it hypoite, one more makes it per 8. If I remember that, then writing it as an acid, the rule remains the same. I'm an 8. Okay? So my acid name is chloric acid, no hydro. Chloric acid. This would be chlorous acid. this would be, you got to keep the hypo there because that is the name of the polyatomic. This would be hypochlorous acid. And this would be perchloric. Of these up here, this is a strong acid, this is a strong acid, this is a weak acid, this is a weak acid. Difference 3, difference 2 between oxygens and hydrogens. So 2 or more, strong. Difference is only 1, weak. Difference is 0, so it's weak. All right, questions on naming acids. On the PowerPoints, there's 2 sets of slides. One has the answers, practice problems. Another one doesn't have the answers, but you can look them up or ask me. So you could try those for homework on naming the acids. All right, then let's talk about strong bases. I'm going to save weak bases for next lecture because, well, we'll talk about them maybe at the end here, and I'll foreshadow into next lecture. All right. Bases. Strong base. Group 1 or group 2, and I'm going to put a little, some group 2s don't work, but the majority of group 2 starting at calcium and below, all right, even magnesium works, but starting at calcium and below, there's little exceptions in there, but group 1 or group 2 metal with a hydroxide or oxygen. So sodium hydroxide, lithium hydroxide, calcium hydroxide, or if they have oxygen, lithium oxide, they're all considered potassium hydroxide, whatever you want. And including, there's one polyatomic in there that's not a metal, ammonium counts too. All strong base means is it completely dissociates in water. It all breaks down. Right? That's all this means. Okay. So, if I take a strong base and react it with a strong acid, so now we're going to do acid base reactions. If I take an acid, a strong acid, let's take HCl. This is the one that's always used. HCl, and I add it to sodium hydroxide. Finish that, OJ. There we go. I'm going to get out 2 products. It's a double displacement reaction. So hydrogen's going to go with hydroxide, sodium's going to go with chlorine, and we're going to get out NaCl plus HOH. Our states of matter are aqueous and a liquid. In case you don't see it, this is water. Just another way of writing water, hydrogen hydroxide. This is sodium with chlorine. We know it as table salt, but the general form is if I take an acid and I add it to a base, I'm going to get a salt. And the definition of a salt is the cation came from a base and the anion came from an acid. And every time a strong acid reacts with a strong base, I always get out some ionic salt and water. My ionic equation, my net ionic equation, every single time is going to be the formation of water if I have a strong acid reacting with a strong base. So let's break this reaction down. Okay. If I break this down, here's my molecular. I want to break it down to my complete ionic. I have one H plus aqueous plus a Cl minus aqueous plus an Na plus aqueous plus an OH minus aqueous that's going to give me Na plus aqueous plus a Cl minus aqueous plus HOH liquid. I then cross out my spectators. Chlorine, sodium gone, sodium, chlorine gone, and I write my net ionic equation. And my net ionic equation for acid-base reactions should be the same thing every single time. An aqueous hydrogen with an aqueous hydroxide gives me water, HOH liquid. Okay. There is one exception to this rule. It always doesn't work out right, but here it is, and you'll see it in the lab. All right, the metathesis lab. And here it is. If I take an acid, and I add it to a carbonate or a hydrogen carbonate. Now, it's a double displacement, so hydrogen's going to go with the CO3. The Na is going to go with the Cl. Okay. So we're going to get NaCl. And this is aqueous here. And this is going to be aqueous here. And we get a second product. And hydrogen goes with carbonate and makes H2CO3. But here's the problem with H2CO3. H2CO3 is not a stable compound. So H2CO3 breaks down into two things. And we don't write H2CO3 out. What we write is we take the two hydrogens and one of the oxygens, H2O, and we're left with CO2 as gas. This is how Alka-Seltzer works. Alka-Seltzer contains a carbonate and citric acid, and when you place them in water, or citrate for that matter, when you place it into water, citric acid donates the proton, and we create the CO2, and that's why Alka-Seltzer bubbles. So if you were to do this reaction in lab, you would see bubbling. This is the reaction if you've ever made the volcano with baking soda and vinegar. Vinegar is the acetic acid donating the hydrogen, and you're creating the CO2 gas. So if we were to do the complete and net ionic equation for this, okay, H plus aqueous plus Cl minus aqueous plus 2Na, and of course we have to balance this. So we need a 2 there and a 2 here, so there'll be a 2 and a 2, just for completeness. 2Na plus aqueous plus CO3, 2 minus aqueous. I'm going to bump these up here out of the way. So this would be H2O liquid plus CO2 gas. Every time, carbonate with an acid. We're going to get out 2 Na pluses, 2 Cl minuses, an H2O liquid, and a CO2 gas. Cancel out our spectators, sodium and chlorine, and we are left with 2H plus aqueous plus CO3, 2 minus aqueous, yields CO2 gas and liquid water. Because they're not aqueous, they don't break down. Okay? Question on acid-base reactions. Okay, let me see here before I... All right, if there's no questions, then homework. So this book does naming acids for a very short, brief thing on page 90, 2.94 and 2.95. You could try those plus the ones on the slides. And then page 198, 4.57 to 4.62, 4.57 to 4.62, 465 to 468. Okay. So that's what we could try for homework. All right. I'm probably going to finish this chapter, I want to say, on Thursday of next week, so we could decide about an exam. Now, as you guys saw, the letter from the president saying that this is pretty much it until the end of the semester. All right, we're going to be meeting online and doing everything online from now until the end of the semester. What he also stated was the grading aspect, where you could take the letter grade or you could change it to a P if you got a C or better, or you could take a W if you fail and all of that stuff, but that's still being hammered out. But what I'm going to do is this on top of that, and you could decide what you want to do, but I'm not going to make the final cumulative. Okay, so we'll just keep taking chapter exams, and wherever we're at the end of the semester, we'll just take an exam on that. Now, my goal is to get to chapter 10. I'm pretty sure I can do it by the time May rolls around. But you won't have a cumulative final, which means that if you're on the pace of being exempt after the first exam, we're not going to have that anymore. Which I apologize for that, but on the other hand, I was thinking of how am I going to do a multiple choice cumulative final, and I figure 100 multiple choices, that's ridiculous. You guys will be so stressed out. So what I'm thinking of doing is that. So it's not going to be a cumulative final because I don't need you doing an online 100, multiple choice exam. Because even if we have, let's say we had 4 lecture exams, that'd be 8 chapters. I mean, at 50 questions, what am I going to do? Ask like 4 questions or 5 questions per, you know what I mean? Like 5 questions per chapter, or 6 questions per chapter. It won't be enough. I'd really have to take it out to like almost 75, 100 questions. Okay. So I'm going to try to make it, like I said, I'm keeping the video short, sweet, so that you can watch them, upload them, have a good time. But that's my plan for now. With the grading, I guess you'll be able to decide what you want. But that's where we'll go with that. As far as I know, the P will be a C or better, but it won't go towards your GPA if you decide to take a P. That didn't sound right. If you decide to take the pass grade instead of the letter grade, your GPA won't be affected. All right, so I'm going to stop the recording.